So hello, everybody. I'm Monica Beckwith, and I welcome you to this session. I'm glad that you all able to make it today, and I'm thankful for Philly ETE to giving me this opportunity. Today, I'm going to talk about GC tuning and confessions that I have over the years of tuning GC. So about me, I'm a JVM GC performance engineer. I do consultancy work now. I have worked at AMD, Sun, Oracle, and I've learned a lot about HotSpot JVM. I'm going to cover these three GCs today, primarily because I've seen these three in production, and also I have a lot of experience with them. So what I'm going to cover today is I'm going to talk a little bit of performance engineering, just to kind of get you a feel of the work performance engineers do. I'm going to talk about garbage collectors, and I'm going to introduce the three that I talked about, the Throughput collector, the CMS, and the G1 GC. I'm going to summarize whatever I told earlier, and then I'm going to talk about tunables. All right, so performance engineering. So a performance engineer kind of helps you make sure that your design and your implementation kind of meets your performance goals that you had come up with, your performance requirements. Now, how do you make these requirements? These requirements could be something that you just pick up from your SLA, from your service level agreements. You know, service level agreements have known to have throughput, latency, response time metrics, right? So you can pick them up. So basically anything that's your non-functional requirement, you can pick them up and you try to make your performance requirements based on that. I'm going to talk a little bit about what metrics to choose, because it's really, really important that you have the right metrics. And I'm going to give an example for GC. You know, when I'm tuning GC, you know, if I'm choosing the wrong metrics, how it could lead to a wrong conclusion. So let's go to that slide. All right. So here, I have 4 systems that are running an application. It's a long-running application, and I captured some metrics. I have the average garbage collection time, pause time, and I have the minimum. So I'm really happy, right? Everything looks good. Average is below what was needed and way below what was needed, and minimum is really, really good. Should I pat myself on the back about my tuning? Not yet. Again, now I'm going to look at number of GCs. I had about 40,000 events, garbage collection events, and my average is 323 milliseconds on system 4. That's really good, right? Again, is it good enough to pat myself on the back? Not yet. All right, here you go. There was a problem, right? One particular GC, or at least the maximum GC, took 20 seconds on system 4. 20 seconds. On every other system, it was about 3 seconds was the maximum, averaging about 2.7 seconds, but one system took 20 seconds. Now, and why was that? When I looked at the GC logs, I found there were 5 full GCs and 10 evacuation failures. I'm going to talk about full GCs and evacuation failures later, but I wanted to highlight something over here. Would I have caught that 20.699 seconds if I would have gone with 99th percentile? No. 99th percentile was 1.04 seconds. Would I have caught that 20.699 seconds if I would have gone with 99.999, the 5 nines? No, that was 19.03 seconds. So basically, if I would have done 99.999999 percentile, then I would have caught that. So don't omit data. First principle of tuning, to not omit any data, because any data that you have and every data that you have is really important for tuning exercise. What else do we need to know about performance engineering? Monitoring, analysis, and tuning are a big part of performance engineering. If you don't have the right monitoring tools in place, you don't have the right profiling tools in place, what are you tuning? Right? You haven't captured enough data to tune anything. So what do I mean by monitoring? So monitoring utilization, CPU, I/O, system, bandwidth, memory bandwidth, Java heap utilization. Then you analyze the utilization. How do you analyze that? Look at the logs. Look at your GC logs, CPU, memory, application log, database logs, right? And then profiling. Don't shy from profiling, right? You do application, system, memory profiling. Java heap profiling will help you with a lot of things. I think I may talk about this a little bit more, the profiling aspect of it, how it can help. So when I'm talking about Java JVM performance engineering, what do? I study, analyze, and tune the JIT compiler, the garbage collector, and sometimes even tuning related to the JDK, the libraries. You can either tune the library, depending on where you're working. If you're working for Sun Oracle, you're tuning the JDK. You're working for companies outside that are using the product, then you tune the application of these libraries. All right, that was very little introduction into performance engineering because I want to spend more time on garbage collectors and give more insight about garbage collectors. So moving on to garbage collectors. So what is a garbage collector? A garbage collector is an automatic memory management unit. So ideally, in perfect world, an ideal GC would be the one that requires minimum footprint. So for example, concurrent CPU usage would be minimal, or native memory would be minimal, and it provides you the maximum throughput, right? The time that you spend in garbage collection is minimum, so it's maximizing your application throughput. And it provides you predictable latency, at the same time, minimal latency. So you need all these things to happen to have your ideal garbage collector, right? So what's the reality, though? The reality is that you have to make trade-offs, right? You cannot have everything, footprint, minimum latency, maximizing throughput. And usually, if you think about your application, you really are chasing one particular thing. So you can prioritize these three, and then you go out of the first one, and then the other things will improve too. It may not be the best possible, but it will improve as well as you're optimizing for your goal. And when you perform a healthy performance engineering exercise, you will meet and exceed your goals. All right, another fun fact: GC cannot eliminate your memory leaks, right? Memory leaks are what you do, your application does. Garbage collector cannot mark an object dead just because it's just there in memory for a long time, right? But it can help you. It can help you by helping you visualize your heap, by helping you visualize your objects, and by helping you being able to profile these things. So GC and heap dump, what I really am talking about. You can look into your application and you can help identify memory leaks, but GC is not going to eliminate it for you. All right, so talking about the trade-offs, right? So throughput and latency. I'm going to concentrate this talk on OpenJDK HotSpot collectors, okay? So throughput and latency are the two main drivers for refinement in GC algorithms. So almost everybody that I have worked for have come to me and said that they want to increase their Java heap, but they fear full collections because they have seen full collections, and full collections have been drastic for them, and sometimes they cannot recover from full collections, so they have tried to push it to some other preferable time, but that's what they fear the most, and they want to increase their Java heap if they can. All right, so let's talk about the GC, the throughput maximizer GC. So what is desired of a throughput maximizer GC? So the quest of maximizing throughput has driven us to parallelization of GC work. So you have parallel collection threads, parallel marking threads, and what else has Throughput driven us to? Throughput has driven us to generational GCs. And a fun fact is that all OpenJDK hotspot GCs are generational. Now, what do I mean by generational GCs? So the GCs are based on this principle that most objects die young. So what you can do is fast path allocate objects into this young generation where you let them die. You age them appropriately, and then you promote the long-lived objects to the old generation, right? And why do all GCs and hotspot have a generation right now? It's because it was observed that single generation, or like the original GC, was not able to scale well. And what happened is that there were so many throughput-related performance challenges that drove the hotspot engineers to generational GC, and now that's the de facto type in hotspot garbage collectors. All right, now you have latency-sensitive applications, and what does that drive, right? Latency has driven algorithms to no compaction or partial compaction. So what does that mean? Time is of essence. When you're talking about latency, you're really sensitive to stop the world pauses, or any pauses in general. So, so what does that mean? If you have free space in your old generation, why do you want to stop your application? Just keep on sweeping it on the fly along with your application, right? So, what else has latency done? Latency has driven us to concurrency, right? Again, do work along with your application. Granted, there's going to be an overhead, right? Because you're using CPU while the application also wants a CPU. So yes, keep that overhead in mind. But so now we have GCs such as mostly concurrent mark and sweep, which does concurrent marking and sweeping. And concurrent marking in G1 is also done along with the application threads, right? So now that being said, fun fact again, is all garbage collectors in OpenJDK hotspot fall back to a fully compacting, stop the world garbage collection, which is also known as the full GC. Tuning can help avoid or postpone full GCs. Again, I said postpone, because tuning can only get you somewhere with certain GCs, and I'll talk about them. All right, so let's talk first about the easiest collector, the Throughput collector. Throughput collector is on by default on server class systems, and it's the easiest to explain. Parallel old is the Throughput collector in OpenJDK hotspot. So first I spoke about Throughput briefly, but let's define Throughput here. Throughput is the percentage of time not spent in garbage collection. So for example, for parallel old, the Throughput goal is 99%, which means that it would like to spend only 1% of your total time in garbage collection. So how does parallel try to achieve its Throughput goal? I'm going to ask you this question because that's the whole point of me giving this presentation. So we'll probably be able to answer this question at the end of my presentation. So let's look at a traditional Java heap. This is kind of similar for CMS as well. It's a contiguous Java heap with contiguous young generation and old generation. So as you can see, young generation is divided into Eden and survivor spaces. Here I have mentioned survivor S0 and S1. I also use terms such as from space and to space. It's easier to explain using from and to, but let's stick with S0 and S1 too in this case. So most allocations happen into Eden, and then the survivors, after the Eden is full, the survivors get moved on to the survivor spaces. After that's the first collection. The next collection would take Eden, next young collection would take Eden and from space, survivor 0, and move all the survivors into S1 or the 2 space. And this keeps on happening back and forth till your objects are aged appropriately. And once your objects are aged appropriately, you tend to tenure them into old generations, the long-lived objects. That's the goal, right? The long-lived objects, the tenured objects are tenured into the old generation space. Okay, here I talk about the same thing that I just mentioned earlier in text. So a couple of things I didn't mention was the allocations and promotions are both fast-tracked, right? So basically there is something called local allocation buffers or local promotion buffers. These are thread local buffers that do lock-free, enable lock-free allocations. Okay, so it's really fast. Now let's look at the old generation for the throughput collector. It's a contiguous space. In this particular scenario, I have shown something that has a lot of promotions into it already. So the occupied space is gray, and the unoccupied, the free space, is no color, I guess. All right, so now we have a to be promoted object 1 that is going to be, that finds, it, it's of a particular size, it finds the space there, it fits in right there nicely, so now the heap looks like this. Now we have second object that's to be promoted, fits in nicely, third object fits in nicely. So what are we observing? So now let's talk about the contiguous old generation. So once your old generation is full, basically when the old generation cannot accept any more promotions, it's time to start a full compacting collection. The parallel old collector that I'm talking about here utilizes parallel stop the world garbage collection threads to help compact the entire heap. How does it achieve compaction? It achieves compaction by copying. So basically, the parallel collector for the old generation is a mark, sweep, and compact collector, right? And what happens at the end of compaction is like all your live objects are kind of in one place, and then you have this free space available for future promotions. Okay. So let's look at this in terms of this particular diagram. So we have Java application threads in gray, and those dotted lines basically mean that that's the stop the world phase right there, where your Java application threads are stopped, and your young generation threads start doing their GC work that's needed to evacuate the young generation and kind of survive move the survivors to the survivor spaces. You will see multiple of those young generation pauses before you will see an old generation pause. But just for simplicity here, I show that the application threads resume again, and then when you have an old generation pause, again, it's parallel and stop the world, and then again your application resumes once your old generation has collected the old generation in its entirety. All right, so moving on to CMS Collector. So mostly concurrent mark and sweep collector is geared towards latency sensitive applications. So the young collection in CMS is similar to what you would see, what I just spoke about with respect to parallel load, the throughput collector. The main difference is actually the CMS part of it. The CMS collector is an old generation collector. So what happens is that when a marking threshold crosses, basically it's an occupancy threshold for the old generation, when it is crossed, a CMS cycle is initiated. The sweep part of the CMS cycle just reclaims space. So whatever is free, dead, is now free space. In space deallocation happens, and then this reclaimed space is kind of mentioned into the free list of spaces. So the CMS collector is not compacting collector. There is a fallback compacting collector, but the CMS is not a compacting collector. So when you have a long-running application using CMS, you will see fragmentation, right? And what happens when you have fragmentation? It basically, you have free space, but your object, the promoted object, is not able to fit into that free space. So then you encounter a promotion failure. Promotion failures eventually lead to full single-threaded compacting fallback collector, right? All right, so let's talk about the CMS cycle itself, right? So so after the old generation, the threshold is crossed, there is initially a parallel stop the world marking cycle. And that is, it's called the initial mark. And then that is useful to help find the GC roots, right? And you start your live object graph, start making a live object graph. Concurrent CMS threads, basically concurrent again means working with the application threads. They help in making further changes to the live object graph and try to trace the objects that are reachable by the roots. Then you have a parallel stop the world CMS threads, the CMS collector threads, that help ensure that any mutation to your live object graph is captured. That's the final step. And then, once you have this pretty graph now, you know what objects are dead. So the concurrent sweep cycle comes in and helps collect these dead objects and update the free list based on the reclaimed space that you have. So how does that look? So here we have the same things. Gray is application thread, white is GC threads, and then I have something, the blue, to show the concurrent CMS threads. And basically you see there's a young GC, just as it's similar to what we saw earlier. Then we have the CMS initial mark threads where everything is stopped to make sure that we have the GC roots. And then we have some concurrent threads to kind of trace the roots and everything. And now between, sometimes during this tracing, you could have young GCs, because your ETE is still getting allocations to it, and it'll get full eventually, and you have multiple young GCs in between then too. So I'm just showing one here. And then after the concurrent marking cycle is complete, you do a final remarked state that stops the world, and then finally you do the concurrent CMS cycle, which is the concurrent sweep, so you can get reclaiming the dead object space. So let's look at the old generation in CMS. Now this is, again, a long-running application here. We have some free spaces. So there's been a lot of promotions to it and lots of deallocations to it. So now we have a free list here that's keeping account of all the free spaces right there, okay? All right, we have the first object that needs to be promoted. Okay, it cannot fit into the first space, so it moves on to the next one, and good. The free list is updated again with all the free things in there. Second object comes along, yes, it fits in the first space. Now there's a little bit space left, so the free list is updated again to point to that free space. Third object comes along, cannot fit in the first free space, cannot fit in the second, cannot fit in the third, cannot fit in the fourth. So what have we observed here? We have observed that although there is some free space in the old generation, our object that needs to be promoted, is not able to fit in any of those free spaces, and we have just encountered a promotion failure, so which will eventually lead to full GCs. All right, there's another thing that I wanted to talk about CMS before moving on to G1, and that was the concurrent mode failure. So what does that mean? It just means that CMS cannot keep up. It has lost the race. So your promotion rates are so high that the CMS cycle could not complete, or even if it's complete, it's not able to free up the space that needs for your promotions to happen. So what can cause? There are lots of causes, but I'm just going to highlight a few of them. So your marking threshold could be too high. So you're not starting the CMS cycle on time. It could be that your heap size is too small. Yeah, I mean, and then there's also, you have high application mutation rate. For example, you could have high allocation rate. There could be spikes in your application behavior. And, all those things can cause the concurrent mode failures. It's really, it's really a big problem with CMS. All right. So moving on to the garbage first garbage collector. So garbage first garbage collector is the newest collector in OpenJDK HotSpot. And it's supposed to be a long-term replacement of CMS. Everybody knows the pain points of CMS, and here comes G1 to save everybody. G1 introduces the concept of regionalized heap. So remember when I was talking about CMS and parallel, I was talking about the heap region being contiguous and also the generations being contiguous. G1, of course the heap is contiguous, but the generations don't have to be contiguous. So, and I'll talk about that soon, and I have diagrams to show that too. So the idea of tuning G1 is that you just have to set your pass time goal and kind of let G1 use it as a hint. So G1 has ergonomics and prediction logic that tries to get you to your pass time goal. It's not a guarantee, but it's kind of like a hint. And G1 will adjust its collections and the generation sizes and the number of regions to collect to try to best meet your pass time goal. G1 also has a multi-phased concurrent marking phase, and I'll talk about that very quickly. The collections are almost all are stop the world pauses. So young and old generation collections are stop the world pauses. Okay, so throughput is a secondary consideration of G1 for G1. Remember for the throughput collector I mentioned 99% was the throughput goal. That means only 1% of the time will be spent in garbage collection. For G1, that goal is 90%. That means 10% of the time can be spent in garbage collection. And that's understandably so, because G1 wants to achieve predictable latencies, right? So throughput is not a primary consideration. With the G1 regionalized heap, it kind of ensures that G1, the generations don't have to be contiguous. So what that means is that when G1 needs to add, G1 has these heap bounds. It has these defaults for minimum and maximum nursery, and of course you're providing your own heap settings. And when G1 has these limits, it can just add a region and claim it to be a young region. So basically there's a list of free regions, and whenever G1 needs one, it'll just pick it up from the list, and it doesn't have to be contiguous for it to be a part of a particular generation. So an occupied region can be Eden, Survivor, Old, and Humongous region. And I'll talk more about Humongous in the next, after a couple of slides. So this is how a regionalized heap in G1 looks like. So I've shown some regions as Eden, one as Survivor, 3 years old, and 2 contiguous regions as Humongous. Okay, so let's move on to the young generation collection in G1. So a region is a unit of collection in G1. So the young generation consists of Eden regions and Survivor regions. And the size of the region is determined at JVM startup. You can, of course, always change it on the command line as well. So again, most allocations, similar principle, right? Most allocations are fast path allocations into the Eden regions. The Survivor regions help in aging objects, which are eventually promoted. It's a similar principle, right? After the age threshold is gone. So the young generation is resized after every collection based on the time it took the current collection and the pass time goal that you had and other factors. So when you're doing an old generation collection also, then you have other factors that need to be considered by the prediction logic. So let's look at the current heap configuration here. And during a young generation collection, the regions are identified, and a young generation collection will always collect its generation in its entirety. Okay? So all the regions in the young generation collection, all the occupied regions will be collected. So there you go. Something survived and something got promoted, and here we have the heap after a young gen collection. Okay, so moving on to the old generation. For G1, the old generation collection consists of all the young generation regions and a few candidate old regions. Such a collection is called mixed collection. And so basically, how do we do that? How do we have these few candidate old regions, right? So the GC ergonomics, the G1 GC ergonomics selects these candidate old regions based on certain thresholds that are a part of the ergonomics, right? And there are some calculations that are done to make sure that most reclaimable space, basically the spaces with most garbage, are collected from the old generation. At the same time, there's consideration given to pass time goal as well. So based on your total number of candidate old regions, the pass time goal, and other old generation collection related thresholds, you could see more than one mixed collection pause. And that is good when your application encounters more than one mixed collection pause back to back pretty much. So for every marking cycle, the initial mark that you see, if you see multiple mixed GCs, that's good. That's a good sign, because that is the old generation being collected incrementally, right? That's what is called an incremental collection. You're not collecting the old generation in its entirety. You're collecting it incrementally. So that's the major difference that you need to know from the Throughput collector, which compacts the entire old generation. CMS doesn't do compaction, but it falls back to a full compacting collector. And G1 does old generation collection incrementally, not in its entirety. So let's talk about the marking threshold. In order to start a mixed collection, it's similar to what we have discussed about in CMS. You have something called the heap occupancy threshold. The term heap and old gen is the only difference here. CMS has old gen occupancy threshold, so it's only dependent on the old generation. G1 is the heap the entire heap, basically. So when the marking threshold is crossed, G1 will start its initial mark cycle. Again, all this is similar to what I've mentioned about with CMS. So when it's marking the root, that'll be an initial mark during initial mark. And then when you're remarking, again, it's the same thing. It's going to be a stop for world pause, because you want to make sure all the mutations to the object graph are captured properly. During the concurrent marking phase, any garbage, this is very, very important to know. During the concurrent mark phase, while it's happening concurrently with your application, any completely filled region, any region that's completely free, like garbage-filled region, can be collected. So if a region is full of garbage, it can be collected during a concurrent mark phase and does not have to wait till the next mixed collection. So for example, this is your current heap configuration. And during our concurrent cleanup phase, we found out that there was a region filled with, the old region filled with garbage. So of course, we can reclaim it right then. Ta-da! All right, so now let's move on from the same heap configuration. I want to demonstrate a mix after the marking is done, cleanup is done. Let's talk about mixed collection. So again, it'll take all the young generation in its entirety and a few candidate old regions. So here, those two regions in green, circled in green, are identified as candidate regions for this particular mixed collection. And there's the heap after the mixed collection was done. Young generation collected in its entirety, candidate old regions collected as well. The few live objects are promoted again to a new old region, and then some objects survived as well. All right, so as promised, talking about humongous objects. Humongous objects are basically objects that are 50% or more, that span 50% or more of a G1 heap region. So these objects, because of the sheer size and because of the basic things needed. So for example, if the object spanned more than the G1 region, then it would need contiguous regions to put it into. So these objects are not fast-tracked into the young generation. They're allocated directly out of the old generation, and now these regions are called humongous regions. So why was this decided to be this way? Ideally, the assumption was actually that humongous regions are going to be short-lived and very few. And since they have to be contiguous regions, heap regions, you don't want to move them around. Now imagine if they were if they're long-lived or whatever, so you're now moving this live, humongous, contiguous regions into, back and forth from Eden to Survivor, and then aging in Survivor and moving into the old generation. So you didn't want to do that, so just move it directly into the old generation and label it humongous. There were other issues with humongous regions and humongous allocations, and and they could lead to evacuation failures. And something's done recently that I'm going to talk about here. So anyway, the reason they would cause evacuation failures is that they have a lot, some applications may have a lot of humongous objects and a lot of long-lived humongous objects. So since humongous regions add to the occupancy, the heap occupancy, so you would trigger your concurrent marking cycle, but you're really not reclaiming anything during the concurrent cleanup, because that's the only time you could actually reclaim a humongous object is during a concurrent cleanup. This is before JDK 8 update 40. And so if it's not dying, you're not reclaiming it, and now it's just sitting there in the old generation, making your heap occupancy go higher and higher based on how many humongous allocations you have. So in 8 update 40, there was a change that is done. So if any humongous region was found to have no incoming references, then it can be reclaimed, basically. So if they're no longer reachable, reclaim it during a collection. So that is a major change for humongous objects that die and not too long-lived. But usually we end up like, if they're long-lived and a lot of them, then you have to change your region size, try to put them back into the young generation and stuff like that. So anyway, that's something to keep in mind. And I'll talk more about this a little bit in the evacuation failure section. All right, here you go. Evacuation failures. What are evacuation failures? Basically, you may have heard two-space promotion failures, or two-space overflow, or all these terms. They all mean the same. It's the same notion. And when we're talking about evacuation failures with respect to G1, what we mean is that G1 could not find a free region to either survive or tenure objects to. So we have sort of survived or tenured objects, but we don't have regions to move them into, right? So that's an evacuation failure. And evacuation failure is very expensive because, if you've already copied objects, for successfully copied objects, for example, G1 will have to, it needs to update those references, right? And the regions have to be tenured. For objects that were not copied successfully, you'll have to self-forward them and tenure the regions in place. So that's why it's expensive. And usually, it's an indication that your application is eventually going to have full, compacting, single-threaded garbage collection. All right, there are tricks to avoid evacuation failures. First of all, do not overtune your application. Do not overload your command line. And never a good idea with G1. G1 has so many things going on, and you are trying to put, force into behavior that you were expecting, but G1 is definitely not needing your help if it can do without all those help that you're providing it. So try to get a baseline without all your overloaded command line. Try increasing your heap space if you can. Check if your humongous allocations are the cause of your problem. Remember, that adds to the old gen occupancy threshold, and you're just triggering these collection cycles in the old generation, but you're not reclaiming much, right? Again, adjust your marking threshold. If that's the case, you can adjust your marking threshold. Too high, then you can risk evacuation failures. Too low, you're just reclaiming nothing, right? Try increasing your concurrent threads. So why is that important? So when your initial mark happens, when your marking threshold is crossed, you do a concurrent cycle. Now, the time that it takes the concurrent cycle to complete, that's a time you're not doing mixed collection, right? So if you put in more concurrent threads, if you can, then you're kind of speeding up this concurrent process, so now your mixed collection can start, because your mixed collection cannot start till your concurrent marking cycle is complete, okay? If you see you have enough space for the old generation, and actually your survivor spaces are not sized properly, or they're not able to, and you have a two-space overflow just because of the survivor spaces, then there's something called G1 reserve %, and basically the default is 10% of your Java heap. So it's actually a false ceiling that where you reserve the memory in case there's need for this two-space. So basically, I think in parallel load or whatever, in the traditional heap layout, you have something similar to that. So this is just specific to G1, which kind of lets you push it up to 50%. So you can have 50% of cushion, of padding space. So if you have an overflow a little bit, you can accommodate in your survivor two space itself. All right, so what have we learned so far? This is a summary. So young generation and young collections. I'm going to summarize young generation collections here. Young generation is always collected in its entirety. So all three GCs that I discussed earlier, they follow similar mechanisms for young collection, right? We always, kind of discussed that. The young collection achieves reclamation via compaction and copying of the objects, right? Also discussed that already. And there are a lot of options for sizing the ETE survivor space optimally, and many GCs also have adaptive sizing. For example, parallel has adaptive sizing enabled by default. G1 has ergonomics that enable adaptive sizing of the generations. Okay. So most allocations fast path into ETE. If ETE is full, you start collecting young collection, else keep allocating. Objects are aged in survivor space, then you promote, otherwise keep aging. Promotions are fast path into the old generation, except for CMS. So CMS promotes to only these fitting free spaces, right? If your promoted objects can fit into a free space, that's when CMS will promote, right? And it's out of a free list, so it's not really a fast path. I mean, not out of the TLabs. That's what I mean by fast path. Fast path are basically those thread local buffers, right? All right. So moving on to old generation, this is the most important difference, right, between all the three collectors. So all three garbage collectors vary in the way they collect the old generation. For parallel old, for example, the old generation is reclaimed and compacted in its entirety. So luckily, the compaction cost is reduced by having parallel worker threads. And unluckily, the compaction cost depends a lot on the size of the live data set. And since at every compaction, the GC is moving live data around. So for parallel, there's no tuning option other than the generation size itself. So you can adjust the generation size and the age threshold for promotion. And that's the only option that's available for you. What about CMS? For CMS, the old generation is mostly concurrent mark and sweep. And the reclamation of all dead objects happen in place. There's in-place deallocation, and the space is added to a free list of spaces. The marking, there's something called the marking threshold, which you can tune. It's right now enabled to be adaptively tuned based on your application profile, but you can fix it manually. Luckily, CMS doesn't do compaction, so reclamation is really fast. Unluckily, a long-running Java application with CMS is prone to fragmentation, like I mentioned, which will lead to promotion failures, which will eventually lead to a single-threaded, full compacting GC. Okay, like I already mentioned, full compacting GCs are single-threaded in CMS. What about old generation collection in G1? For G1, the old generation regions are mostly concurrently marked and incrementally compacted. And I have explained that before, but this helps us a lot. So it helps us with optimizing the old generation collection. So you can it's kind of tuned to your pause time goal. The fragmentation part of it is not untunable in G1 case. So for CMS, remember, we couldn't tune fragmentation out of it. But in G1, we can. It's up to us. The fragmentation tuning is how much fragmentation you can tolerate. It's kind of up to it. There's tunables in G1. Unluckily, in G1, sometimes you encounter promotion failures that I mentioned earlier, and it's when G1 runs out of regions to copy live objects to. And such evacuation failures, I already mentioned that, and it leads eventually to a full compacting GC. Again, full compacting GC is single-threaded, just like in CMS case right now, at least. But when you appropriately tune the old generation space and the old generation collections, you can help avoid evacuation failures and help keep full GC at bay. full GC, single-threaded compacting full GC is not the norm for G1. G1 has multiple tuning options so that GC can be adapted to your application needs. So let's talk about the tunables. So what's the goal with respect? So based on all that I said, I think it's pretty clear. The goal is to only promote objects after you have aged them appropriately, right? You're trying to delay that full compacting collection. Although it's parallel threaded, you're still trying to delay it as much as you want, as much as you can. And you just want multiple young collections is what you're looking for. So that's the goal. So what are the tunables? Everything related to aging objects and generation sizes, all the options that you know of. The new ratio, max new size, survival ratio, tenuring thresholds. Tenuring thresholds are the ones that help you with the aging, appropriate aging. Those are the age thresholds, basically. So what do we need to remember when we are tuning a throughput collector? So there's something, the adaptive size policy, I mentioned that briefly. It's something that helps with adaptively sizing your generations, right? And applications with steady-state behavior don't really need adaptive sizing policy anyway. And one thing you need to remember is any overflow, because of wrongful sizing of your generations, will get promoted into the old generation. And remember, we're trying to minimize promotions to the old generation. So you should try to provide larger survivor space for long-lived transient data. In most cases, young generation sizing has the most effect on throughput. So one of the goals that you should have is try to keep your GC overhead to less than 5% with respect to the throughput collector. And how would you do that? This young generation sizing, those options that I mentioned earlier, aging of objects appropriately, that'll help you keep your GC overhead to less than 5%. CMS. So you notice the pattern again? It's the same thing. It's only promote objects after you have aged them appropriately, right? So tunables, again, everything related to aging objects and young generation sizing and everything that I mentioned earlier, it still applies here. There's something different though. There's something called the concurrent threads and the concurrent marking threshold, right? So those are the two options that can help you tune CMS. So you can fix the concurrent marking threshold to the desired size if your adaptive marking threshold is not helping, and the concurrent threads will help speed up the concurrent mark and sweep cycle. All right, moving on to we're still in CMS. Okay, fine, good. Things to remember in CMS. Premature promotions are very expensive in CMS. And that could lead, and does lead, to to fragmentation, which leads to promotion failures. So what can we do, right? We know it's going to happen eventually, and we're just going to try to push it out as much as we can. You can reduce the CMS cycle duration by adding more concurrent threads. I think I mentioned that before, but this will increase the concurrent overhead. You can manually tune the marking threshold, which is kind of fix it up by providing that initiating occupancy fraction to whatever percent you want of your old generation. And then you say just use the initial occupancy only. So use that fixed value for all my CMS cycles. Okay, now moving on to G1. So the goal is totally different with G1, okay? You gotta get the ergonomics to work for you. Don't over-tune it. And you should know the defaults. If you're using G1 Collector and you do not know the defaults, you are in a lot of mess, because there are so many defaults that can help you tune the collector to the way you want it to work. And if you don't understand them, if you don't know them, then that's even worse. Okay, so what are the tunables? Pause time, there's a lot of, I'm just gonna read it. Pause time goal, heap size, max and min nursery size, of course, we all know that. The concurrent and parallel threads, the marking threshold itself, the number of mixed GCs after marking, right? The liveness threshold for the old generation. So that determines how expensive a particular region is for collection. If you have more live objects in one region, that is more expensive because you're moving live objects. That's what you're doing. You're achieving compaction by copying, right? Okay, garbage toleration threshold. So again, since I have a lot of my liveness threshold is really high, I'm okay with those regions not being collected. So I'm okay with having whatever garbage does. So that I'm okay with certain fragmentation, right? That's what that is. Max all regions to be collected per mix cycle. So I want my only X number of all regions to be collected at a maximum per cycle, because I don't want you to go collect more regions per cycle, because I'm going to distribute my incremental collection. You can do that with G1. All right, so again, things to remember with respect to G1. Know your defaults. I'll keep on saying that. Understand, for example, I'm just giving one example here. So for example, the understanding your G1 heap region size. It could be any factor of 2 from 1 MB to 32 MB. And G1 actually strives to get it about 2048 regions. And how does that help us? Remember that humongous object? That's dependent on the region size. So if you don't know what your region size is, pretty much any object could be humongous, you know? So you don't want that. So you want to know the defaults again. You can change it, of course, right? But if you don't know what it is, then what are you changing? Anyway, so fixing the nursery size will meddle with the GC ergonomics. Remember, there's a lot of ergonomic things and a lot of tunables, right? So if you're fixing the nursery size, what are we trying to do? We're not trying to let G1 increase or decrease it. So basically, by default, nursery can move anywhere from 5% of your heap to 60% of your heap. So if you're fixing it to a particular size, then it's not able to be adaptive enough. So you're either promoting way more than you need or way less than you need or whatever, you know. So try to let the baseline be as simple as possible. Don't set really aggressive pause time goals. So what do I mean by that? So G1 strives to meet it. It may not be perfect. It is not perfect. So it strives to meet it. And what happens is that if you have aggressive pause time goals, it'll size the regions or add so many regions such that your GC overhead will increase. So keep that in mind. And spend time, lots of time, taming your mixed collections. Mixed GCs are incremental old generation collections, and try to get them to work in your favor. All right. So what do I mean by taming mixed collections? Adjust the marking threshold according to your live data set. Again, too high, too low. Too high is you're going to lose the race. Too low is you're just spinning and not collecting enough, not reclaiming enough. Adjust your liveness threshold. Remember, every region has this liveness threshold that you can adjust to. So you're trying to make a region, so you're trying to collect less expensive regions is what you're trying to do. Adjust your garbage toleration threshold. It helps G1 not get too aggressive with mixed collection. Again, you're okay with certain fragmentation. You're okay with not touching these old regions that are deemed expensive. So that you're okay with that garbage in those regions, right? By default, that one is, I think, 10%. I'm not sure. Distribute mixed GC pauses over a number of mixed collections. So you have something with G1 that you didn't have with any other collector. You have this incremental old generation collection. Use it to your advantage. Distribute your mixed GC pauses over a number of mixed collections. So after marking cycle is complete, let there be a multiple of mixed collection pauses, and let their time per each be minimal, right? So how do you do that? You adjust your mixed GC count target, and you can change your maximum old region threshold %. So basically what that means is that per mixed collection, I only want X number of regions maximum to be included in that collection. So, you know, the candidate regions, I only want X number of candidate regions. You can specify that on the command line as well. And there are, of course, these defaults that I don't remember right now. All right. Very good. So further reading, of course, my favorite book, Java Performance. It's also available in Chinese. And there are so many things that you can learn from. One of the good things about this book is that it's documented. Everything that I want to go back to, I look at this book and it's documented in there for us. And Charlie Hunt is a great friend and a great person, great performance engineer, great speaker. So that's a great book, well-written book. What do I like to suggest as further reading? Again, John Masamitsu is another great person, and it's amazing. All his blogs are so interesting. Even now, I go back and I read them, and it's just very interesting to me to read his blogs. I have written some articles on G1. Most of my presentations, I try to put it up here on SlideShare. And of course, mail archives. Go dig up on mail archives if you're interested in using any of these GCs, or if you're interested in learning about the development of these GCs. Sometimes, you won't. I mean, I'm subscribed to both of them, and the GC dev is like they're a bunch of fixes, right? but sometimes there's some discussions that are very interesting. So go get in on those discussions, even as just a spectator or whatever. So that's all I have for you. I have some time for questions, or we can talk about it later as well, if you have any questions, because I know it's the best presentation, so no questions at all, I'm sure.
A question on the G1 collector. We have an application that holds a significant amount of stuff in basically hash maps, and I wasn't sure if G1 would be a good fit, especially like regarding the humongous objects.
Especially like what?
With humongous objects, some of these hash maps are very large. Would that be an issue with G1?
What's the percentage of humongous objects to all the the objects?
It's probably at least half the heap.
Huh?
It's at least half of the heap.
Half of the heap?
Yeah.
And
like
how long do
several
they live?
gigabytes, so say like 6 gigabytes.
How long do they live?
As long as the application is running.
You'll be fine. Just make sure your old generation can accommodate them.
Okay.
So basically, a marking threshold should be able to take that as your live data set, that and any other live data set that you have. Keep your marking threshold to that, and you should be fine as long as your old generation can accommodate. So G1 needs headroom, right? Because we talked about how much garbage you can tolerate and all those things. So it needs a little headroom, and of course, it's a compaction via copying, right? So the incremental collections are happening. It needs free space too. So if you can give that to it, and if you are, I'm guessing you are because you have 50% of large objects, so you should be able to give that, and you should be fine with G1. Just try the, what's your heap size?
Probably 16 gigs.
16?
Yeah.
1/6? Okay, so you probably will be like, what, 4 megs or less regions or whatever, right? So yeah, just try, just try G1. Just try. Give it and if you're not worried about pause time, are you worried about pause time?
Yeah.
How much?
Would like to balance it out, I guess.
What's the max? What's the worst case?
Well, so we were using CMS before, and we did some work to reduce the heap size, and we had some excessively long pauses with CMS. Once we got the heap size down a little bit, those pause times went down. I don't know of like a specific goal that the customer has in mind for it, but
is it 1 second?
Yeah, I guess that would be okay.
CMS worked for you said, right?
Sort of. We were getting concurrent mode failures.
Yeah. So I think with 16 gigs and with 50% like live object space, you should be fine. Keep your goal to your worst case. Keep your pause time goal to your worst case. So when on the command line, say whatever that thing is, max GC pause millis, go to your worst case, which is 1 second. Say 1,000. Just put that on your command line. Let's see what G1 does. Hopefully it'll be good. Otherwise, email me or whatever.
Okay, thanks.
Yeah. Thank you very much.